Hello and welcome back to the Cracking FAANG YouTube channel. It has been many months since I've made a Leetcode video, but more people are watching the channel now, so I figured I would just make some more videos. And what better way to start than with my favorite problem of all time, Leetcode 269 Alien Dictionary. Let's read the question prompt. There is a new alien language that uses the English alphabet. However, the order of the letters is unknown to you. You are given a list of strings, words from the alien languages dictionary. Now, it is claimed that the words are sorted lexicographically by the rules of this new language. If this claim is incorrect, and the given arrangement of words, the string in words cannot correspond to any order of letters, then return an empty string. Otherwise, return a string of the unique letters in the new alien language sorted in lexicographically increasing order by the language's new rules. If there are multiple solutions, return any of them. Okay, that one is quite the mouthful. Let's look at two very basic examples before we get into the more concrete one, because it is actually kind of hard to go over. So let's look at example 3, which is the easiest one, which is that we're given that these words, Z, X, and Z. And essentially what we want to do here is we know that assuming the order is right, Z will come first in the dictionary, then X. Then we actually get another Z, which means that this order is not possible because we already know that Z comes before X, but now if Z is coming after X, then this isn't possible. So that's why the solution here is actually a empty string, because we have this weird kind of dependency that X comes after Z, but it also comes before Z. So this is the case where it's actually invalid. So that's why it's empty. Here we have Z first and X second, and this one's fine. We know that X must come before Z, so the order is just ZX. Now, let's actually look at a more complex example. We won't go through the whole one because it will take way too long to write out, but we'll get the general gist, and we'll talk about the actual intuition to this problem. So let me wipe away all of this text, and now let's kind of just look into example number 1. Test. Okay, so we read the question prompt and we looked at two very basic examples to kind of set the theory. But let's look at the actual more detailed example to figure out how we might want to approach this problem. Now, we know that the ordering here is assumed to be lexicographically sorted. Of course, we saw previously where it wasn't, in which case we needed to return an empty string, but we need to go forward through this problem with the assumption that actually the strings are lexicographically sorted. And if that's true, then we can actually use the position within each of the words to figure out the letter ordering. And instead of looking at this jumbled mess here, let's look at the English language and see how we can do this. So let's take two different words. The first one will be adapt, and the second one will be adult, right? So adult. So they're both the same length, and what you'll notice is they actually start with the same characters. So we can actually kind of mirror the logic of our example here. So if we were trying to derive the order of our characters in the English language, obviously try to forget that you actually know the order of the English characters, and we were told that adapt comes before adult. Well, how can we figure out some things here? Well, obviously the first two characters aren't going to tell us anything because they're the same character. So if they're the same, we can't tell which one comes before it. Obviously, we know that adapt comes first, adult comes afterwards, right? So then we would compare these two, but we don't get anything out of that because they're the same character. And we're actually going to be able to use the same logic in our jumbled characters, because if they're the same character, we can't derive an ordering here. So for the D's also, this is the case because they're the same character. We don't know what comes before. So basically, we want to look for the very first divergence here, which is this A and this U, right? This is the first point where the characters are not the same. Similar how T and F here are the first characters in these two that aren't the same. In adapt and adult, A and U are not the same. Now, we know that adapt comes before adult, right? So if this is guaranteed to be first and this is guaranteed to be second in the dictionary, then we know that A comes before U, right? In the English language. And obviously this is true. And for our example here with WRT and WRF, what we would derive from doing the same exercise, so WRT and WRF, sorry for the terrible writing, is that T comes before F in our dictionary, right? So what we can do is we can build this comparison for basically every single pair of words in our dictionary here. So what we could do is we can compare WRT with WRF, and then WRF with ER, and then ER with ET, and basically try to derive all of these mappings. So what you'll notice is there's actually a graph that's going to be built here, which is going to take a character, and we're going to map it to all of the characters that come after it. Now, this is a hard problem, and you've probably seen that it's tagged as a graph problem. So this is where I'm kind of going to break the fourth wall and tell you that to solve this, we're going to need to, one, build a graph, which is what we've already started to do here. And the second is we need to traverse this graph with a DFS, and we're going to use a topological sort here because we actually need to detect cycles. You could do it with a BFS. My solution just uses topological sort. If you don't know what that is, I have some videos on topological sort on my channel. Look for course schedule 1 or course schedule 2. They explain how to do this really easily. And what this DFS is going to allow us to do, once we have the graph, we can actually traverse starting from each word, and we can actually build our graph. Now, one important thing to note here is that if we build our graph in the way that we just did, where each character, we keep a list of all of the characters that come after it, if you think about how topological sort works, and this is the point where you want to pause the video and watch the other videos if you don't actually know how topological sort works, remember that we're DFSing. And if we DFS starting from A, the endpoint will be the last kind of like character in the graph for A, right? However we traverse the graph. And that will actually be the first solution we reach. So say, for example, in the English language, it's Z. We would actually return Z before we return A, because remember, in topological sort, it's a DFS. So you'll go all the way down until you can't go any further, and you'll get to Z, and then you'll start going back up the chain, and eventually you would return A, which would mean that our order is actually going to be reversed, right? We'd return Z first, and we'd get A last, which is not correct because actually A comes before Z. So what we actually want to do is, instead of building our graph, with all the characters that come after a character, we actually want to do it in reverse. So instead of storing for A that U comes after it, we're actually going to store all of the characters that come before that second character. So for U, we're actually going to store that A comes before it. That way, when we do our topological sort DFS, then we're actually going to get the correct order, and it saves us having to reverse our result string in the end. Okay, so this is where I want to stop. I'm not going to go through the entire example because it's going to take me forever to write it out, and it's just not clear. I'm probably going to trip up. It's easier to really just look at this in code. This is a hard level problem. You ideally should be able to just follow the code at this point if you're solving this one. It's a lot easier than you might think. The code is not that hard. It's really the same topological sort template we've used in other videos. So basically, what you need to get at this point is that we're going to build a graph, and it's going to be such that the character is going to be in reverse, right? So when a character is determined that, A, it comes before U, we're actually going to store in the graph that for U, A comes before it, instead of storing that A, U comes after it. So we're going to reverse our kind of adjacency list here, such that when we do our DFS, it will return things in the correct order. Now, if you don't believe me, then please, by all means, do it the other way. And then when you see it, you submit your solution, you're actually going to get your answer in reverse, and it's not going to be accepted, and you need to reverse the string. You can do it either way. I just prefer to just build it and not have to reverse it later. Anyway, that is enough for rambling. This problem is hard enough as it is. Let's now go to the code editor and actually type this bit up. So I will see you there. Okay, we are in the code editor. Let's now type this up. So what is the first thing that we want to do? We want to build our graph here. And remember that we want to build this for each of the characters in our words. So what we're going to do is we're just going to initialize our graph. So we're going to say char, and it's just going to be an empty list for all of the characters in our words. So we're going to say for word in words, for char in word, right? So this will just create our empty graph, and we're going to need to populate it. So what we're going to do is we're going to say for word 1, word 2 in zip words of words one. So what this is basically going to do is it's going to compare pairwise words, right? So if we have like word 1, word 2, word 3, word 4, this is going to compare word 1 and word 2 and word 3 and word 4, and so on, right? Because they're already assumed to be sorted, so we just compare pairwise ones. We don't actually need to do word 1 with word 2 and then word 3 and word 4. We just need to basically just zip pairwise ones. So that's what we're going to do here. So for each pair of words, we want to take the shorter word. That's basically what we're going to go for. And the reason for this is obviously app will come before apple in the dictionary, even though they have the same starting. Because app ends first, it actually comes before it in the dictionary, right? And this holds true, for English and also in our new language here. So we want to make sure we're traversing over the shorter word. Obviously, if we used apple, then we could have an out of bounds index when we try to look in that index for app. So that's why we do the shorter word. So let's see, for I in range of whatever the minimum of length of word 1 and the length of word 2 is, we want to basically go index by index. And remember, we're comparing. If the two letters at those indexes are the same, then we don't really do anything. We just continue because we don't get any information from that. Otherwise, what we want to do is that we just want to get the ordering from when those two diverge. So for example, remember we had adapt and adult. The fact that A and D are the same doesn't tell us anything, but the fact that A comes before U does. So that's how we're going to derive the order. So we're going to say if word 1 of I does not equal to word 2 of I, when we have a divergence, we basically want to say self.graph of, remember we're going to do it in reverse. So it's going to be word 2 of I. We're actually going to append word 1 of I. So this is the point where we're actually building for that letter. So remember in our example, adapt and adult, we know that A comes before U, but this would give us the reverse order when we DFS, because remember DFS, you'll go all the way down and then come back up again. So we actually want to say that A comes before U. So we're going to store for U here that A comes before it instead of for A that U comes after it. So that is what happens. As soon as we find our first divergence, we break, because after this point, there's no guarantee that the words after it are going to give us any information. So it's only at the first divergence that we actually get something. So we want to break here. Now, what we want to do is we want to, in this for loop, we want to have a check here for an edge case. And in this edge case, for each of these words, if actually the length of word 1 somehow is longer than the length of word 2. So for example, this would be the case that you get apple coming before app, which shouldn't happen because apple is actually going to come after app. Of course, this is in the English dictionary. But you cannot have this. So this actually means that our words, which are not guaranteed to be sorted, this is a case where they're not. So we just break because the words were not given to us in the correct order. So if the length of word 1 is actually greater than the length of word 2, we're going to return an empty string. Now, you want to do this at the end of the for loop. In Python, you can actually throw an else at the end of for. In other languages, I actually don't exactly know how to do this, but basically as soon as this for ends, then you want to check that this word 1 is not actually longer than word 2, because in this case, your words aren't actually sorted, so your assumption is broken. Okay, so this actually builds the graph. Now what we want to do is we want to just do our topological sort, and remember that typically the way that we do this is we have a white set which represents the nodes that we haven't visited yet. We have a gray set which denotes the nodes that we're currently visiting, and we have a black set which defines the nodes that we've already visited. And this is the way that we actually keep track of whether or not we have cycles. If something's in the gray set and we visit it again, then that means that we have a cycle in our graph, which means that we just exit because we can't do anything with a cycle. So we're going to say that the white set is actually just going to equal to a set of self.graph.keys. So we're going to put all of those starting nodes. The black set is going to be empty, and our gray set is just going to be an empty set as well. We want our result, which is going to be a list here, which we're going to append the characters to. And now what we want to do is we want to say while there's something in the white set, we want to get the next value out of it. So we're going to say next iter white. So this will get us the next value in our white set. Now what we want to do is for each node, we want to basically run the DFS to figure out the order. So we're going to define the DFS function in a second, but we're going to say if not, and this DFS function is going to return true if something was actually able to you were able to derive something out of it, and false if there's a cycle. So if not DFS, so basically if this part returns false, then we want to return an empty string. So we're going to say, we're going to pass the white set, the black set, the gray set, the current node, and the current result. And if our DFS function actually throws a false, then we want to return an empty string, because that means that we found a cycle and it's not possible. The last thing we're going to want to do is just join our result together, and that should be the end of it. Okay, so pretty simple. Now we just need to define the DFS function. So we're going to say def DFS, and this is going to take self, white, black, gray, node, and res, right? Okay, so the first thing that we want to do is actually move our current node that we're working with from the white set into the gray set to indicate that we are basically visiting it. So let's just quickly define a move vertex or move node function. So we're going to say move node. This is going to take the node we want to move, the current set, and the target set. So what we're going to do is we're going to say current dot discard the node, and we're going to say target dot add the node. So we're going to remove the node from the current set, which is usually going to be the white set, adding it to the gray set, and then we'll also do the same when we do it for the gray set and the black set. So this is just a helper function, so we don't have to write this code multiple times. So anyway, back to the DFS. The first thing we want to do is actually move the vertex. So we're going to say move the node from the white set into the gray set to indicate that we are visiting this node at the moment. So remember, the gray set stores the nodes that are currently being visited, and this is how we're going to detect cycles. So now we want to do, so for each node, so we'll call it for parent in self.graph of the current node. So basically for each of the characters that come before our current character, we're going to say if the parent is in the black set, that means that it's actually been fully explored. The black set in a topological sort defines nodes which have been fully DFS'd already, so we actually don't need to do anything there. So we can just say continue, we're good to go, we can move on to the next one in our for loop. We're going to say if the parent is actually in the gray set, that means that we've hit a cycle, because if a node is in the gray set, that means that it's currently being visited, and if we return to that node, that means that we've hit a cycle. So at this point, we can return false. Otherwise, we want to just run the DFS. And again, we need to watch out for cycles. So we're going to call it in exactly the same way that we did here. So we're going to say if not self.dfs of the white set, the black set, the gray set. We want to pass in the parent this time and the current result. So if this returns false, then this if statement will trip, and we want to return false because that means that we found a cycle later on in the DFS. So the last thing we need to do is, once our for loop ends and we have successfully gone through our DFS, we need to move the current vertex that the current node. Why do I keep saying vertex? The current node that we're visiting, we need to now move it from the gray set into the black set to indicate that it's been fully explored. So we're going to say self.move node, and it's going to be from the gray set this time into the black set. And we want to now append the current node that we just visited, because we need to actually add it to our result. And obviously this will have been done in the children, which means that it's now time for this one to be added to our results. So the last thing we want to do is just return true, because we were able to go through the DFS without any problems. And that's it. So this is a lot of code. Let me just double check I didn't make any syntax. So DFS, where is it? Oh, self.dfs, because it is a method on the class here. Okay, cool. So this should be fine. Let's submit it. What happened? Submissions. Okay, accepted. Perfect. Now let me just close this and we can talk about our time and space complexity. Test. Okay, so let's now look at the time complexity. So there's two parts to our solution, and the first part was actually building the graph, and the second part was traversing it. So if we look at the time complexity of building the graph, let's kind of go back and look at what we did. So we essentially went through for each pairwise word and compared every character by character. And we did this for whatever the minimum length was. So the total number of operations across our entire body of words will actually be just the sum of each of the words. Because remember, we do them pairwise, so we'll just compare the words as we go along. And this is actually just going to come out to be big O of C, where C is the length of all strings in words added together, right? Because that's the total number of characters we're actually going to need to compare, because we just do it index by index. So we need to do that for all of them, and we just add them all together. So in the worst case, that is what's going to happen. So that is for the actual graph building part. And then we have the traversal, which is just a standard topological sort. And remember, this is V plus E, where V is the number of vertexes, and E is the number of edges in the graph. So that gives us a total time complexity of, so big O of C plus V plus E. So that is going to be the time complexity there. And for the space complexity, the graph is what really takes up the most time complexity here. Space complexity. So remember, to build the graph, we need basically, it's similar to the time. We have V vertexes and E edges. We also have these gray sets here, but the space complexity from building the graph will actually be much higher asymptotically than these sets that we use and whatever we need for the solution. So the space complexity is really bounded by the size of the graph. So that is Leetcode 269, Alien Dictionary, one of my favorite problems to do. Once it kind of clicks, it's a really cool problem. I enjoy topological sorts, a bit complicated to explain. Hopefully I did a pretty decent job of explaining it. I think the code is a lot easier to read and understand than just looking at me trying to explain it. Anyway, hopefully that helped you. Hopefully I didn't ramble too much. It's my first video back in a long time, so I am very, very rusty at lead coding and explaining these things, but hopefully you found this helpful. If you did, why not leave a like and subscribe to the channel? Otherwise, thank you so much for watching and have a great rest of your day. Bye.